So today we're going to start out by finishing up 2.2, which there isn't very much left. I think there's one question. And then we'll spend most of the rest of the class on 2.3. So we're going to look at an example of a company that produces t-shirts. And the company has two types of costs. They have what's called a fixed cost, and they also have variable costs. So an example of a fixed cost might be the cost the company has to pay to rent a warehouse facility every month. It doesn't even matter if they use it. If they sign a lease saying they're going to rent it, they have to pay $200,000 even if they don't make anything. All right? They're just paying to have the building. So that's fixed. Now, the variable cost is going to be how many shirts this company makes. It costs them $1.50 for every shirt that they design and create. Maybe that includes the cost to buy the blank white t-shirt and then to print on it. Whatever they do to it, it costs them $1.50 to make their product, and then they sell it for $4. So they're selling it for more than it costs to make it. So eventually they'll make money, but this fixed cost of $200,000, that's a big investment up front. So let's find complete graphs of two things. We're going to find an equation that represents the costs for this company, and we're going to find an equation that represents the revenue, or the money that the company takes in from selling their product. Now, whether we're talking about the variable cost or the revenue that the company makes, it depends on what? What does the variable cost, what controls the variable cost? Yeah?
How many shirts they make.
Right, how many shirts they make. That also controls the revenue, how many shirts they make. The number of shirts has no effect on the $200,000. That's just fixed cost. So we're going to pick a variable to represent the number of shirts that we make. You could use S for shirts, but sometimes my S looks like a 5. That can be confusing. So let's stick with X. So let's let X equal the number of shirts. And we're going to find cost as a function of X and revenue as a function of X. All right, so how about Piper? You think you could give me an equation that represents my costs, variable cost of $1.50 per shirt and a fixed cost of $200,000?
Wait, two different equations?
No, all in the same equation.
Okay.
That'll all be my cost.
So 200,000
Okay.
plus 150x.
Yeah. So we have 150x, or 1.5x, plus 200,000. There's my fixed costs. And Tiana, could you give me an equation that represents the amount of money that I make from selling the product?
4x.
Good. 4x. And now they want us to graph those. Now, when we look at this 1.5x plus 200,000, Tom, what is that 200,000 if you think about it in terms of like y equals mx plus b?
It just means shift the whole thing upwards by 200,000.
Well, yeah, it's like a vertical shift of a line up 200,000 units, so it basically puts my y-intercept at 200,000. So I'm going to try my y-intercept, I'm going to try my y-max even higher. Okay, I'm going to need a pretty big window. So 1.5x plus 200,000, that's fine, I typed it on y2. I didn't need to. And 4x. As long as you put one of them in y1 and put the other one in y2. Now, x is the amount of shirts we make. We don't know how many shirts we're going to make, but there is a minimum. What would be the smallest number of shirts we could make? Bill?
To make a profit or just to make shirts?
Just, you know, we have a company and we're gonna make shirts this month. What could be the smallest number of shirts we end up making?
0.
We could make 0, right? Maybe the equipment breaks, we don't have any equipment. So 0, and the max, well, that we don't know. Okay, let's try 100, I don't know, let's try 50,000 shirts. Let's try that. Now, why min? We can't have negative revenue. That wouldn't make sense. So our revenue is always going to be a positive number, and our cost is definitely going to be a big positive number. So we're never going to have negative cost or negative revenue. Y max, again, I would go above 200,000. I would try maybe, let's try like 275,000. Let's hit graph and see what we have. So there's our profit, and there's our cost. How does the slope of the profit compare to the cost? What's happening? Yep.
The profit slowly begins to grow and grow more.
Yeah, the profit's kind of catching up to it. Profit has a steeper slope, which means at some point, what's going to happen here?
They're going to intersect.
They're going to intersect. And if we want to find a complete graph of the two equations that represent cost and revenue, that would be an important thing to have on the screen. So that's not a good window, right? We're going to have to set probably a little higher. Let's try making 100,000 shirts, and let's set our Y max at 350,000. Right, so we're just playing with it until we get the intersection point on the screen. So there is our profit. I think we're going to be okay this time. Yep, and there's our costs. So that's a good window. So the directions said find a complete graph. There you go. That's what I would write down. X min, X max, Y min, Y max. And here's the actual graph. Okay, any questions on that? Now, this point is something, this point is something special. Anybody know what that point's called? It's where the cost and the revenue are the same. Yep, Tiana?
Is it the breaking even point?
Yeah, it's the break-even point. So the break-even point, if you want to think about it algebraically, is where cost equals revenue. That's what the break-even point is algebraically, where your cost and your revenue are the same, and your profit is basically 0. You haven't made money, you haven't lost money.
So after that, would you make money, like going upwards?
Yes.
Make a profit?
Yep. So anything after the break-even point is profit, anything before the break-even point is loss. Yep. So we already kind of answered this, but when you're looking for the break-even point on a graph, it's where the two graphs what? Yep.
Intersect.
It's where they intersect. We kind of already mentioned that. So for a graph of cost and net revenue, where is this point? It is where the graphs intersect. Now let's use that graph we just came up with to answer a question. Find the number of shirts the company in example 1 must sell to break even. So remember, break even. Let's go back up to our formula. This is the formula that tells you where you break even. It's where C of x equals R of x. So, before we even use the graph, let's do it algebraically. All we have to do is substitute in what the cost is and what the revenue is and solve. Set C of x equal to R of x. All right. C of x, was that the 1.5x plus 200,000? Okay. That's C of x. And what was R of x again?
4x.
4x. And let's solve. So we have 200,000 equals 2.5x, and then divide each side by 2.5. And if you divide by 2.5, you will get 80,000. You can just double check it, that's what it is. So setting cost equal to revenue and solving for the variable tells me it would be 80,000 shirts. Any questions on solving for a break-even point algebraically? Okay, let's do the same thing graphically. So I already have it all set up. Okay, I think graphically is more time consuming because you've got to type it in Y1 and Y2. You've got to set your window, and now you've got to do what we're doing right now. I did the algebraic one way fast. How do I find an intersection here? Anybody remember what we press? Quizlet?
Isn't it second trace and then 5?
Yep. So we do second, press the trace button, and now it says pick a point on the first curve. We got the blue one. Pick a point on the second curve. We got the red one. The guess doesn't really matter because they only cross in one spot. It'll find it. And let me just make that a little bigger. Maybe you can see it. But it tells me the intersection point is when x is 80,000. What's my cost to produce 80,000 shirts? Well,
$80,000.
Well, we have a fixed cost of 200,000 already. So it's got to be at least, it's got to be more than that. Yeah?
$320,000.
Right. My cost to produce 80,000 shirts is $320,000. What's my revenue if I sell 80,000 shirts? Yeah?
0.
Not my profit.
Oh yeah, then it's 80,000. 320,000.
320,000. So my cost to produce 80,000 shirts is 320,000. My revenue when I produce this many shirts is exactly the same. So now I'm at the point where my profit is 0. If I sell more than 80,000 shirts, we start making money. All right. So any questions on that one? And that's it for section 2.2. All right, so that was just about break-even point and really learning to solve for an intersection point. All right, so 2.3. So this is on solving linear and quadratic equations, mostly algebraically. So we're not going to be using the calculator as much in this section. But just a reminder of a few things from Algebra 1, what an equation is. Okay, an equation is when you have an equal sign between two expressions. They can be numerical expressions, meaning there's no letters, or they could be algebraic expressions, meaning there are letters. But an equation is when you put an equal sign between two expressions. If your equation, say, uses the variable x, you could say you have an equation in x. That just means you have an equation that uses the letter x. So if I gave you directions like on the test, and I said write an equation in L, I'm asking you to write an equation using the letter L. So maybe it's a problem about length. Usually we pick a letter that makes sense with what we're trying to find. When you're asked to solve an equation, solving an equation means to find the value or values that make the equation true. Generally, when we're solving linear equations, you have one solution. When we get into quadratics, think about how many times it can cross the x-axis. You could have up to 2 solutions. And then higher degree polynomials can have even more. But solve means to find all the values of x that make it true. An identity is a special type of equation that is true no matter what value you plug in for x. Most equations aren't like that. Lots of equations only have, maybe one or two values that make it true. But in an identity, any value makes it true. Can anyone tell me why is this equation an identity? What makes it an identity? Yeah, Amanda?
Because when you like distribute it to 3 and then subtract 1 from it, it's equal to the side.
Yeah, you get exactly the same thing. If you distribute this out, you get 3x plus 3 minus 1. Well, that's 3x plus 2 on the right, and you have 3x plus 2 on the left. If you've got the same thing on both sides, it doesn't matter what you pick for x, it will always work. That's an identity. Okay, compared to something like that, that's a conditional equation. 2x equals 10. That equation could be true or it could be false. It depends if you pick the right value for x. And so just two different types of equations, an identity and a conditional. The equations we're going to work with mostly today are conditional, meaning there is a specific answer or answers. Questions on that? So we're going to start out by looking at simple equations, linear equations, so no exponents. And then we'll start to look at quadratics. Probably not going to spend a lot of time using the quadratic formula to actually plug numbers in and solve, because I think I went over one in the homework that did that. What I'm more interested in now is kind of where does that formula come from? Right, so that's kind of what differentiates the class that you guys take from like a CP4 pre-cal. Okay, the difference with honors is, yes, I give you a formula and you're expected to know how to use it, but you're also expected to understand and be able to explain where the formula comes from. Like, why is it negative b plus or minus the square root of all that stuff? Like, why? Where does it come from? So that's what we'll take a look at. Sometimes in Algebra 1, when you start solving equations, the teacher has you check your answer or verify that your answer is right. So when you want to check to see if your answer is right, you just take and plug in your answer back into the original problem and see if you get a true statement. Okay, so let's practice just checking an answer. So this would be kind of a tough equation to maybe solve for us right now, because it is a cubic, especially without a calculator. But we're not going to try to solve it. I'm going to tell you one of the answers, and I just want you to check that it works. That's all. Okay, so I want you to verify that negative 2 is a solution. All right, so how about Alejandro, how would I check that negative 2 is a solution to that equation?
You replace x with negative 2.
Which x?
All of them?
All of them. Everywhere you see an x, replace it with negative 2. And it's a good idea to do it in parentheses, because when you raise a negative number to a power, that negative has to get raised to the power with the number. So we get negative 2 cubed minus negative 2 plus 6. And that's the question, does that equal 0? That's what we're checking. Logan, what's negative 2 cubed? Negative 8. Good. Negative 8. And Rose, what happens with a minus 2?
It's addition.
Becomes addition. All right. And Tyler, negative 8 plus 2?
Negative 6.
Negative 6. And of course, negative 6 plus 6 is 0. So we ended up with a true statement, which means negative 2 is a solution. Is it the only solution? I don't know. I'd have to check. We know cubics can cross the x-axis up to 3 times. So there could be 2 other solutions. But we at least know that that is one of them. Okay, any question on that? All right. So linear equations in x, okay, meaning using the variable x, look something like this. Ax plus b equals 0. The a is like a slope, well it is the slope, and the b is the y-intercept. The slope and the y-intercept can be any real number that you want, except the slope can't be 0. You might be saying, well yeah, slope can be 0, that's just a horizontal line. True. But that's not called a linear equation, that's called a constant equation. So if you make a 0 and you wipe this out, and you write something like y equals 2, that's a horizontal line, that's called a constant equation. In order to have a linear equation, you have to have a non-zero slope. So let's just jump right into a linear equation and solve it. It's not going to be quite as simple as ax plus b equals 0. But if we do a little bit of work, we could make it that simple. So there's our equation. Which again, you could multiply all this out, put everything on one side, and make it look just like that. So this is linear. How about, Gianna, what would my first step be to solve this?
Distribute the 2 and 3.
Yep. Can you tell me what I would get when I do that?
4x minus 6 plus 3x plus 3.
Good. All right, so first step would be to distribute. How about Mac? Can you give me my next step?
You put the x on one side.
Even before we start moving things from side to side, something else we have to do first.
Like
Yeah, let's combine like terms so we get everything together on the left. Can you combine all my like terms together on the left and tell me what I get?
7x minus 3 equals 5x plus 2.
Yep. So the 7x minus 3 is what you get when you combine everything together. Now, how about Janelle? What could I do next?
You could move the x to one side.
Okay, and which way do you want to move things?
Subtract 5x.
Okay, let's subtract 5x and 5x. And Madison, what else can I do at the same time?
Add 3 to each side.
Yeah, in Algebra 1 I probably wouldn't do 2 things like this at the same time, but we should be able to handle that. That gives me 2x equals 5. And divide by 2. And we're done. So that's solving a linear equation. We could check it, we're not going to check it. But that's the answer. X equals 5x. Any questions on that? So let's take a look at 2 more things about linear equations, and then we'll look at quadratics. So we're going to take a look at solving an absolute value equation. Most of the time, these types of equations have 2 solutions. So we got to look at how do we get both. The first thing we have to do is make sure that our absolute value expression is isolated. What I mean by isolated is this. Let's say this was your problem. That's an absolute value that is isolated. There's nothing else on the same side as the absolute value outside the bars. It's just an absolute value. Everything else is inside. That's good. This is not good. That's an absolute value expression that is not by itself. So if we were going to solve something like that, the first step is to minus 3 from both sides. So we get the bars alone. Okay. Same thing if you had a number in front. 6 times the absolute value of 3x plus 2. That's no good. It's not isolated. Divide each side by 6 to cancel out the 6. Okay, so first step is to make sure the absolute value is isolated. Now, we're going to split it into 2 problems. And I want you guys to focus on what's in here. What does 3x plus 2 have to come out to make this equation true? Yep. Yeah, either 3x plus 2 has to come out to 4. That would make the equation true. Or, what else could 3x plus 2 come out to? Yeah,
-4.
could come out to -4. So I'm going to write down what we just did. So when we're splitting it into 2 problems, the first equation, that you guys did this without me even explaining it, is the same as the original problem, except you take away the absolute value bars. 3x plus 2 equals 4. Because if what's inside here comes out to 4, and you take the absolute value of it, you get 4. Now, the second equation, it's very similar to the first one, except we have to change the sign of the number on the other side. So that's why it says the second equation is the same as the original, without the bars, and we negate the number on the other side. That means change the sign. So either what's in the parentheses can come out to the number on the other side, or what's in the parentheses, or what's in the bars can come out to the opposite of the number on the other side. And I'm not going to actually solve this one. I'll do a different one. Any questions on that idea? Okay, bless you. So, is that absolute value isolated on one side? Yes, it is. It doesn't have like a times 10, or it doesn't have a plus 6. It has nothing else outside the bars. And the other thing you should check before you even start the problem, is 5 a positive number or a negative number? Positive. If you have this, you might as well just stop. Because whenever you take absolute value never comes out to what kind of number? Never comes out negative. That's a no solution. You can't have absolute value equal to a negative number. So if you notice a negative on the right-hand side, stop. Okay, we don't have a negative on the right-hand side, so we're ready to split it up. So we want 2x plus 3 to come out to what? Okay?
5.
Yep. We either want 2x plus 3 to come out to 5, because the absolute value of 5 is 5, or we want 2x plus 3 to come out to, yep, Emily? -5. And that will also work. Now we just solve each equation separately. So here we're going to get x equals 1. You can check it, but it works. X equals 1. And here you're going to get x equals -4. And those are both answers. If you only had one of them, you would get half of it. But you need both to get full credit. All right. Any question on solving an absolute value? Okay. So one more thing, and then we'll look at quadratics. So the last thing on linear equations is an application, and it's a mixture problem. So just to kind of explain what the setup is going to be for this kind of problem, you're going to have two different liquids, and we're gonna mix them together. So maybe you'd have, like, let's say we're trying to, like, working with rubbing alcohol. Maybe we have a 60% strength of rubbing alcohol, and we have an 80%. So we have 60 and we have 80. And I want you to mix the two together to make 73. So I need one that's 73 for whatever reason. And I want to have exactly 2 gallons of it. So how much of each one would I have to mix together to make exactly 73% strength and have 2 gallons when I'm done? So that's going to require setting up 2 equations. One equation has to do with your amounts. Amount 1, the amount of your first solution, plus how much of your second solution equals the total. But that equation doesn't do anything with the concentrations. That's going to be the second equation. One equation is for the amounts. The second equation has the concentration in it. And it's set up very similarly 3 times in a row. The concentration of your first solution times how much of the first solution you used, plus the concentration of your second solution times how much of the second solution you used. And that has to equal the concentration of your final solution times the final amount that they want. So those are going to be the 2 equations that we set up. And because we're dealing with 2 things, we're going to have 2 variables. Normally 2 variables isn't okay, but it is okay as long as you have 2 equations. That's called a system. Okay, so we're going to have a system of equations. 2 variables, 2 equations. And we're going to solve it with substitution. All right, so a little bit of a review on how to do that is kind of built into this as well. So here are the 2 solutions we have. And they've already picked variables for them. Solution A is the 10% solution. And solution B is the 25% solution. And even more specifically, let's let A be how much of the 10% solution we're going to use, how many liters. Let's let B be the number of liters of the 25% solution we're going to use. So A and B are volumes in liters. I want to mix the 2 together so that I end up with 15 liters. And if that's all you knew, then there's a lot of answers to that. Well, how could I get 15 liters? Well, I could mix 14 and 1. I could mix 13 and 2. I could mix 10 and 5, 5 and 10. There's lots of things I can mix to get 15. But the key is I also want it to be exactly 12%. So let's see if we can set up our 2 equations and solve. So how are we representing how many liters we are going to use of the 10% solution? Any guess? How are we representing how many liters of the 10% solution that we need? Yep.
Would be 0.18.
So that's a concentration.
Okay.
We just want a variable to represent the number of liters needed in the 10%. Well, they've already given us the variables. So I'm basically just asking you to read it up for it. which variable do they tell us to use for the 10% solution? And I said these are going to represent volumes.
Would it just be A then?
A. So A is the amount of the 10% solution that we need. And how many liters are we going to use of the 25% solution? Yeah, Logan? B. And we know when we combine the two together, how much solution do we want to have in the end? Yeah, Kevin?
15 liters.
15 liters. So there's our first equation. A plus B equals 15. Now we have to set up an equation that deals with the concentration. All right. So concentration times amount plus concentration times amount equals our final concentration times our final amount. Now we just have to fill it in. Piper, what's my concentration for the first solution?
10%.
And how would you write that as a decimal?
0.1.
Good. So 0.1 times, and Tiana, how much of that solution are we going to use?
12%.
So that's our final concentration, but I mean, how many liters do we need of the 10% solution? How are we representing that?
I don't know.
Good.
Won't we put X?
We already have variables picked, so we don't want to use a third variable. So we want to stick with letters we already have. Yep, Jaya?
Would it be A?
A. That's the amount of the 10% solution that we need. So again, these are amounts, A and B. Tom, what's my concentration of the second solution? That was given, so that's not anything we have to find. That's the final solution. That's when we mix them together. What's that? Yep, how would you write that as a decimal? 0.25. Okay, so that's the concentration of the second solution. Times, Alejandro, how much of that solution do we need? B. So concentration of my first solution times how much of it, plus concentration of my second times how much. Now, this is the final product. What's the concentration of my final solution? Kristen?
0.12.
0.12. And how much of that do I want to have?
15.
15. Okay, we can multiply 0.12 times 15. I'm just going to write it down off to the side. So the next time I have to write this equation, I write 1.8. Okay. Now, this is equation 1. This is equation 2. Now we have to use substitution to solve this. So let's substitute for A. I'm going to leave everything else just the way it is. And what could I fill in for A using equation 1? Yeah, Matt?
15 minus B.
Exactly. 15 minus B. So that's substitution. Solve one equation for a variable, plug that into the second equation. 15 minus B. Now let's do this out and solve for B. So we're going to get 1.5 minus 0.1B plus 0.25B equals 1.8. What's negative 0.1 plus 0.25? Okay.
Would it be 0.240?
That would be negative 0.01.
Oh, okay.
But this is negative 0.1. Yep.
0.15.
Yeah, good, 0.15. So we have 1.5 plus 0.15b equals 1.8. We can bring the 1.5 to the other side. What's 1.8 minus 1.5? Tyler?
0.3.
Yep, 0.3. And my last step, divide each side by 0.15. What's 0.3 divided by 0.15? Alejandro? 2. Good. So B is 2. That means we need 2 liters. That's the amount. It's 2 liters of this solution. And how many liters would we need of the other solution? Well,
13.
13. Okay. So if you mix 13 liters of solution A, 2 liters of solution B, you will end up with exactly that. Right, so a little bit advanced for a linear equation because it was 2 of them. It was a system. Still something you do in Algebra 1, but much closer to the like middle, not right at the beginning.
Can you go all the way down?
And there are other methods besides substitution. I think you could use elimination, but I think substitution was probably the easiest one on this.
How'd you get 2?
0.3 divided by 0.15. That just comes out to 2. Any question on that? Yeah.
Where did you get the 0.1 from at the beginning when you distributed?
The 0.1 right here?
No, like the whole, yeah, that one.
Yeah, same one. So
Oh.
the 0.1, that comes from the 10%. It's the concentration. We always have to write our percent as a decimal. Same way we had to do it when we did an interest rate formula. Yep.
Where did you get the 15 minus 50?
The 15 minus b? So that comes from rearranging this equation by subtracting b from both sides. So you get a equals 15 minus b. So it's a rearrangement of that equation. And then we substituted that in for the a right there. Yes. Yep. Yep. All right. Anything else on that one? All right. So, last thing we're going to look at. So quadratics, those are written in the form ax squared plus bx plus c. Again, the a, the b, and the c can be any number you want, except don't make a 0. If you make a 0, you've effectively just done this. That's not a quadratic. That's linear. So, one way you can solve a quadratic, besides the quadratic formula, kind of a simpler way, involving 2 sets of parentheses. Anybody remember the name of that method we can use, Lil?
Factoring.
Yep, we can factor. So again, this isn't intended to be a full-blown lesson on factoring. That's something you spent probably 2 or 3 days on in Algebra 1. We're going to do an example in about 2 minutes, and that's really all we're going to cover for factoring. Okay, but you do need to know how to factor. So the very first thing, and I kind of said it when I gave you a hint at what I was asking about with the name of the method, is the parentheses. You always start with 2 sets of parentheses for a quadratic. Right, so let's see if we can solve this one. 2x squared plus 5x minus 3 equals 0. And then the first thing we like to do is usually figure out what's going to go as the first term in each set of parentheses. Now, actually, one thing we should check first is to make sure it's already equal to 0. And it is. Okay, so you really want to make sure it's equal to 0, and you want the squared term to be positive. That's how factoring is traditionally taught. And this one is set to do that. So anyone think they can give me my first term in each set of parentheses? Yep, Logan?
You want 2x and x.
Perfect. 2x and x. What about my signs? Positives, negatives, or one of each? Yep.
One of each.
It is one of each. Could be a minus plus, it could be a plus minus. It does make a difference where you put them in this problem. I just tried minus plus. Now we need two numbers that multiply to give me 3. And 3 is prime, so not a lot of options. Yeah.
1 and 3.
1 and 3. I'm going to just put them in the order that she said them. Let's see what happens. 2x times 3 is 6x. I'm foiling the outer and the inner to check. Negative 1 times x is negative x. That gives me 5x. Is that what I wanted to get in the middle? Perfect. And then negative 1 times 3 is negative 3. Okay, so we factored it. That's the hard part. Now we have two factors, and their product is equal to 0. What do we do with each of those factors? Well,
We separate them into separate equations and make them equal 0.
exactly. Take each one, set them equal to 0, and solve. So you get x equals a half, x equals negative 3. And those are our two answers. Any questions on that factoring method? All right, so the last thing we're going to look at is what happens if you can't factor it. Well, that's where we can use the quadratic formula. So the quadratic formula gives us a way to solve this equation for x. But what I want to look at, and this will be the last thing we do, is how. Why can we, what is this negative b 4a squared, where does that all come from? Minus 4ac all over 2a. Well, it comes from starting with a quadratic equation, like you wanted to solve it, and the a, the b, and the c would normally be numbers. Okay, but we're going to do it very generically, like they're all letters. And the way we can figure out what the quadratic formula is to complete the square on this equation. It's exactly the same steps as completing the square with numbers. But people that don't really understand how to complete the square well, when you throw letters in, they get very confused because there's no numbers. We just have to use the idea of completing the square. So, first thing we have to do when we complete the square is we always put something on the other side. Anybody remember what we always put on the other side? About Janelle? Do you remember what we put on the other side when we complete the square?
Would it be like the C?
The c. Always put the constant on the other side. Normally it's a number, now it's a c. How would you move that c to the other side?
Subtract it.
Subtract it. So we would have ax squared plus bx equals negative c. Now, the next step when we're completing the square is we always like the coefficient of x squared to be a certain number. Does anyone remember what the coefficient of x squared always has to be? Yep.
1.
A 1. What could you divide everything by here that would make this a 1?
A.
A. So let's divide everything by a. A, A, A. So now I have x squared plus b over a x, leave a little space, equals negative c over a. Now we're ready to complete the square. We put the constant on the other side, and we've ensured that x squared has a coefficient of 1. To complete the square, it involves doing something with this. That's the coefficient of the linear term. Does anybody remember the two things that you're supposed to do to that to complete the square? Yep.
If you have it, then square it.
Yep, exactly. You take half of it. So if b over a is our original, b over 2a represents half, and you square it. That's what we need to add on both sides. Plus b over 2a squared, and plus b over 2a squared. Now, because of what we just added, that always makes the left-hand side factor very nicely. It has to factor into two things that are the same. So it's going to be like x, x, and we need two things that are the same. I'm going to erase this, and I'm just going to write it up here, but I'm just trying to show you what it is. What could you put here and here? So when you multiply them together, you get b over 2a squared. And it has to be the same thing here and the same thing here. Yeah.
B over 2a.
Exactly. It would be b over 2a and b over 2a. And I promise, if you FOIL this out, you'll get exactly what you have where I just underlined. So it's x plus b over 2a squared. I'm not going to write it as x plus b over 2a, x plus b over 2a. We'll just shorten it up. And on the right, all we could really do is we could square this fraction. This stays the same. How about, Tom, what do you get when you square the numerator in that fraction?
B squared.
Yep, b squared. And how about when you square the denominator? What do you get there? Gabby?
4a squared.
4a squared, yes. Now, these two fractions can be added together just like any other fractions. But in order to add fractions together, what do you have to make sure you have?
Same denominator.
Same denominator. So what could I multiply the bottom by to make it the same as this other one? Yep.
4a squared. Or 4 squared. No. I'm still on. I thought I had it.
You're close.
Close.
Very close. 4a. 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 Look at what just happened. Minus 4ac. b squared minus 4ac. So you're kind of maybe starting to see a little bit of the quadratic formula. So this side, I'm just going to copy it over again. This side, I'm going to write it as b squared. I'm going to put the b squared first. Minus 4ac. All over. Common denominator. It's not 2a, it's 4a squared, but that's okay. We're going to see what happens in a second. Now, how would you get rid of this exponent of 2? How do you cancel out a square? Alejandro?
Square root.
Square root. Take the square root, take the square root. Watch what happens. Now you have x. Almost have x by itself. There's one more thing we need to do to get rid of that, but we're almost there. If you take the square root of what's on the right, you can't really do anything with the top. It's just the square root of b squared minus 4ac. But what's the square root of 4a squared? Yep,
Now it's 2a.
2a. Square root of 4 is 2. The square root of a squared is a. And the last thing is to take this and put it on the other side. How would you do the opposite of a positive b over 2a? Yep, Alejandro?
Negative b over 2a.
a negative b over 2a. So when this moves to the other side, it becomes a negative b. Think about that, negative b plus or minus the square root of b squared minus 4ac. That has a denominator of 2a. That has a denominator of 2a. So it's all a denominator of 2a. And that's where the quadratic formula comes from. So every time you use the quadratic formula, you're really completing the square. It's just all built into the formula for you. Now that we've proved where it comes from, we don't have to go through and prove it again. We just have to be able to use it. And I think I did one in the homework practicing quadratic formula already, so we're not going to have enough time to practice another one. All right, let me put up homework for tonight. So page 88, I think that's a break-even problem. So 35 to 39, that's like all the same kind of thing. And then page 96, that's on solving linear and quadratic equations. So we'll take a look at that first thing tomorrow. Just a reminder that I am after school for extra help. Not tomorrow, Thursday. After school Thursday. But you're also welcome to come in period 1, 4, or 9 if you need to see me for anything else.